Hi there. My name is João Marcos, and I am a logician who enjoys living somewhere in the hopefully non-empty intersection between philosophy, math, and computer science. What I find absolutely fascinating about logic is the foundational role it plays among the academic fields. Through logic, we may understand and regiment the underlying structure of argumentation, be it in natura, namely in natural language, or modeled through a formal language. Interestingly, logic allows you not only to do things, but it also allows you to show that something cannot be done. It allows you to prove some true things, and also allows you to prove that there's no proof. Well-known examples of the latter situation are the so-called independence results. Among those, we may count problems that were open literally for millennia, such as the independence of Euclid's parallel postulate, the unsolvability of some ancient straight-edge and compass problems, the unprovability of the continuum hypothesis in Zermelo-Fraenkel set theory, or the incompleteness results in arithmetic. Usual pedestrian instances of those problems in logic include the independence of certain statements in a given axiomatic theory. Other, not unrelated, kinds of negative results involve, for instance, incompatibility results, which show that certain principles cannot all simultaneously hold under pain of allowing arbitrary conclusions to be drawn from that. Or even inexpressibility results, namely, results that show that a certain constant or a certain concept cannot be expressed within a certain language. Some old school idealistic philosophers still like to think of logic as the investigation of the truth, in the same way as they think of ethics as the investigation of the good, and think of aesthetics as the investigation of the beauty. These are probably the same people who repeat the mantra about logic being characterized by three sacred old logical principles, but would be pressed if they had to give adequate definitions of those very principles. I like to think of logic primarily as the study of logical inference, the study of entailment, the study of certain varieties of so-called consequence relations. Those consequence relations are directly connected to the quest of establishing judgments concerning the incompatibility of certain positions. For a simple example, we say that B follows from A if a certain A is incompatible with denying B. This is the matter of which logical principles are shaped. Science. Science is investigated through modeling and theorizing, and logic allows you to directly study these models and theories. Non-classical logics are oftentimes born from one's dissatisfaction with models and theories induced by classical logic. They may also aim, though, at extending or restricting the expressive resources of a certain logic. The addition of modal operators, for instance, is a typical way of making a logic more expressive. And the addition of truth values provides a way of helping tune the class of operations that may be defined starting from a certain given primitive object language. Think of propositional logic and its logical constants, the connectives. One may claim that their meaning is regulated by way of appropriate logical principles. Take negation. It obviously involves some notion of opposition, some notion of inversion. But what does it mean to say that a certain connective is a negation? Intuitionist logicians disagree with classical logicians on that matter. Given a sentence A and its negation not A, an intuitionist, more generally a paracomplete logician, will not insist that one of these, A not A, ought to be asserted, proved, verified, or even true. There might be in a given theory, say, no evidence towards A, nor evidence towards not A, no proof of either. Paraconsistent logicians take the dual path. They are willing to admit models in which neither A is denied nor not A is denied. One could have both such sentences present in a theory. More importantly, for a paraconsistentist, it might be possible to assert both A and not A while denying some sentence B. This relaxed attitude towards contradictions, namely, defending that not might fail to be interpreted as a contrary forming operator, gives rise to the failure of the so-called principle of explosion. This simple act of rebellion on the part of paraconsistent logicians opens the door to great many surprising consequences, or lack thereof. Take the example of disjunctive syllogism, the survival principle according to which, if you are driving really fast on an autobahn and find a bifurcation meaning that you may turn either to the right or to the left, and you notice that the right-wing path takes you to eternal perdition, then you must turn left-wing as quick as you can. If you're a paraconsistent logician, however, this general principle is idle. Maybe you're okay with A or B because you do not see reasons to rule out the path of A as an option. And maybe you're also okay with not A because you fail to see reasons to rule it out. In that case, you will not immediately see reasons for choosing the path of B. Alright, that might take you to perdition, but then it might not. For a classical logician, all contradictions might be equal. But for a paraconsistent logician, some are more equal than others. In fact, if from A and not A, you may infer B and not B, and vice versa, then from A and not A, you may in particular infer B. Et voila, you would then recover the principle of explosion. Now, what if there is some reason for one to be indeed willing to recover the principle of explosion, at least in some particular cases? Say that it is that serious. If you do not take the path of B on that road, you will have no chance of survival. Well, if you could only be sure that A behaves consistently with respect to negation, that is, if you could only be sure that asserting A is not compatible with asserting its negation not A, then a gentler form of disjunctive syllogism would be recovered. From A or B, together with not A, together with some warrant that A behaves consistently, you would be able, just like in classical logic, to infer B. Now, that's the foundational underlying philosophical insight of the so-called Logics of Formal Inconsistency. To start with, within classical logic, the situation looks pretty much black and white. Given a sentence A, one may be willing to assert it or to deny it. You may assert it by the affirmation A, and given the meaning of classical negation, you may deny it by producing not A. If you try to assert both A and not A, you're in darkness. anything follows towards the bottom. On the other hand, you cannot simultaneously deny both A and not A. Excluded middle reigns towards the top. In a paraconsistent logic, however, darkness is not the only possible outcome of conflating A with not A. At least some negation inconsistencies will happen to be tolerated. Now, while this might seem to open the way to sheer madness, the Logics of Formal Inconsistency brings some discipline, as well as some extra expressivity to the language. While in classical logic it makes no difference to add the explicit information that a certain sentence behaves consistently with respect to negation, as all sentences do, in a paraconsistent logic, this does make a difference. For instance, if you add to A or B and not A the premise that A behaves consistently with respect to negation, then B would indeed follow, just like it does in classical logic. A gentler form of explosion is present. From A, not A, and consistent A, anything may be concluded. Note that the ability of internalizing consistency in the object language, in the form of a consistency connective, as in this example, is an important feature. While not all paraconsistent logics enjoy such a feature, many paraconsistent logics that have not been originally formulated with such an expressivity concern in mind turned out to have that power to internalize consistency at the object language level, turned out to be logics of formal inconsistency. Let me illustrate this with colors. Say that A is cyan and not A is magenta. By combining both, you produce blue, but do not go all the way into black. Say now that consistency of A is yellow. Combining cyan with yellow, we have green, a kind of strong, in some cases classic-like affirmation. Combining magenta and yellow, we have red, a kind of strong and in some cases classic-like negation. Notice that any addition of one of the primitive colors to the combination will again take us all the way into black. Combining a strong affirmation with the primitive negation just does that. The same holds for the strong negation combined with the primitive affirmation. And the same can be said about the weak inconsistency given by A and not A when combined with the warrant in yellow that A behaves consistently. The three assertions are just not jointly compatible. Now, for what reason should you be interested in studying these fantastic beasts? For what reason would paraconsistent logics and non-explosive negations deserve any bit of your attention? And why should you worry about making such peculiar logics even more expressive by adding a consistency connective? Well, the first obvious answer is that of the mountain climber. Because they're there. You cannot make a certain class of non-classical logics go away by refusing to talk about it. For one, there are other families of logics that already presuppose paraconsistent reasoning. For instance, relevance logics, which are logics aiming to deal with certain paradoxes of entailment. Contradictory logics, which are logics containing contradictory theorems. And some connexive logics, a distinguished class of contra-classical logics. There are also non-trivial philosophical stances that presuppose securing a final control of negation explosion. Some remarkable examples are dialetheism, Meinongianism, and maybe fictionalism. In fact, even science seems to be willing to tolerate a certain amount of contradiction. Our best theories in modern physics, for instance, do not seem to share an obvious, consistent common ground. Now, what about LFIs, the Logics of Formal Inconsistency? Well, these seem to be pretty dense in the class of paraconsistent logics. There are natural examples of paraconsistent logics characterized by logical matrices, by modal semantics, by simple bi-evaluation semantics, by reasonable proof systems, or by appealing algebraic semantics, all of which turn out to have a primitive consistency connective, or else to allow for a consistency connective to be defined. The first operative paraconsistent logics in the literature, those designed by Stanisław Wierzchowski, by David Nelson, and by Newton da Costa, all turned out to allow for the expression of consistency at the object language level. Even a family of non-monotonic paraconsistent logics which is not much into dealing with consistency explicitly, such as the so-called adaptive logics, have their meta-theory based on the same foundational result in which a gentle form of explosion has a role, the so-called derivability adjustment theorem, the result that tells us how consistent reasoning may be recovered given the addition of appropriate assumptions. Remember that example about disjunctive syllogism? What can the LFIs help us with? Well, first of all, they clearly demand us to get a better grip on the logical principles. There are more things there, my dear friend, that are dreamt of in your philosophy. Directly related to that, the LFIs allow you to better understand the meaning of negation. It is when something is missing to you, be it peace, material comfort, health, freedom, or negation consistency, and yet you can talk about it, that you can fully grasp its real value. If you're already convinced that an LFI might be just what you need, what life challenges and opportunities are out there? The same as ever. Differently from intuitionistic logic, which seems to have won the competition for the hearts of most paracomplete logicians, if you dualize your worries, there seems to be no single one-size-fits-all system of paraconsistent logic. And why should there be? So one, may I say, classical problem in the literature on paraconsistent logic consists in finding a system with a good character, devising a nice paraconsistent logical system. There is little chance that this problem will be solved for good, simply because the meaning of nice is dynamic, and there might well be, for each task at hand, a better, more appealing system. Talking about dualization, the class of LFIs is very easily and naturally dualized into the class of LFUs, the so-called Logics of Formal Undeterminateness. Do you want a simple logical system for dealing with glutty reasoning? A three-valued logic might be what you want. You want to allow for gappy reasoning too? Make it four-valued. In either case, you should stop to ponder. Do I want this logic to be an LFI, or do I want precisely the opposite? Notice that if your logic is not an LFI, you might have models, not just for some contradictions, but for all of them at once. You should stop and think if this is what you want. Do you want intersubstitutivity of provable equivalence some sort of replacement theorem, go for a Kripke semantics or a neighborhood semantics. Some very interesting modal paraconsistent negations are out there. In fact, any normal modal logic may be presented in a language that extends positive classical logic simply by the addition of a modal paraconsistent negation. No primitive boxes or diamonds, no primitive classical negation. You may indeed motivate modal logic precisely as a way of studying modal negations. A consistency connective is often available for such paraconsistent modal logics. Yet, in some of them, a classic-like negation will simply be inexpressible, even with the help of such consistency connective. Should consistency always be a subsidiary connective, one whose very existence is only justified by this auxiliary role in helping a paraconsistent negation attain its lost perfection? That is, helping it to behave more like it does in classical logic? No. There are logics which do not contain a paraconsistent negation, but in which inconsistency may be captured by a sort of connective for accidentality. Something happens by accident, if it is the case, but could have been otherwise. In addition, there are other different, richer semantic frameworks that allow for the meaning of consistency connectives to be described without any reference to a paraconsistent negation. For instance, in terms of judgment aggregation for collective decision making, in terms of interpretations involving information flow or cognitive attitudes. There's a whole world out there. If you're interested in formal semantics, you might well want to contribute some novel interpretation for the LFIs. People do it all the time. You should be careful, of course, not to think that your preferred interpretation is the only one that makes sense. If you're a proof theorist, have you already found the killing deductive system for your LFI? Have you even looked at the ones already available in the market? So, now that you have your preferred semantics at hand, what good features can it boast? Is it compositional? What about your preferred deductive system? Is it analytic? How does it fare in terms of proof search or proof complexity? If you put your algebraic glasses on, do you like what you see? Does the consistency connective behave as you would expect? Say you're a computer scientist. Is your preferred paraconsistent logic already an LFI? Does it have good applications to problems in your field of research? Databases, for instance, are very prone to contain inconsistencies. Does your paraconsistent logic with a consistency connective even have a useful computational interpretation? And yes, what about mathematical applications and real-life applications? Allow me some final words to wrap up this monologue. The class of Logics of Formal Inconsistency was identified and systematized while I was doing my PhD thesis roughly 2 decades ago, and have now conquered the world. Not convinced? Want to know more about them? Advised on related literature, perhaps? Feel free to get in touch with me